This is a lesson of the conversion of alcohols to alkenes by dehydration, which means the removal of water. And in this lesson, you'll be using three mechanisms for doing your dehydrations. One of them is the E1 elimination reaction. The other one is an E2. And finally, you'll also be doing rearrangement reactions. Okay, and after the rearrangements, then you'll proceed to do E1 eliminations. So let's go ahead and see if there are examples in this lesson so that we can illustrate the three mechanisms. Okay, in this particular question, you're asked to draw something very complicated. So let's go ahead and start by drawing the alcohol. So first question is butanol. And it's an alcohol, so I'll leave that till the end right there. At the second position, you have an isopropyl group, which is also called systematically a 1-methyl ethyl group. Okay, at position number 3, you have two more methyls, and at position number 2, you have an ethyl group. Okay, and then we'll come in here and we'll draw and complete the alcohol, just to know what we're starting off with. Now, sulfuric acid is actually the catalyst for this reaction, and remember the heat is what drives the equilibrium for making alkenes. So let's go ahead and add all the hydrogens. Okay, and we'll hit arrange. And while the program is doing that, let's go ahead and add a proton to be our acid catalyst for this reaction. Okay, and so what happens in all of these reactions first is that oxygen gets protonated. So we'll use chemistry to go ahead and take electrons from the oxygen. Okay, and we'll hit arrange. Okay, now in this reaction, okay, this is actually called a neopentyl system. And let me go ahead and turn off the hydrogen so you can see the structure completely and see why we call this a neopentyl system. Okay, first of all, you have a primary carbon, okay, or a primary alcohol. And in the vicinal carbon, you have 3 alkyl groups right here. Okay, so in this particular reaction, you just can't go ahead and ionize off water because you have a primary carbon. So primary carbocations haven't ever been observed like that. Okay, so the next best thing you can do then is you have to go ahead and get the electrons from the vicinal positions. Now, if these were hydrogens, you could go ahead and get electrons from those hydrogens. But since they're not, then what you have to do is you have to go ahead and as you're eliminating water, you have to shift over the electrons from one of these 3 alkyl groups. So in this case, you have a primary alkyl group, a tertiary alkyl group, and then a secondary alkyl group. And the one that will most likely get shifted over is tertiary over secondary, and secondary over primary, and primary over methyl. Okay? If we had a hydrogen in these systems like this, hydrogen would probably be the one that shifts over first, or we could just go ahead and take its electrons and form a double bond directly. Okay. Now, the reasons why the shift will actually occur with the T-butyl group are actually many. Among them are that, for instance, if you look at a Newman projection of that T-butyl group, since it's the largest one, it wants to be anti to the leaving group right here. So that's one reason. Okay. And another reason also is if you consider the mechanism that we're going to propose to do, which is essentially to ionize off oxygen, okay, and then shift over the alkyl group at the same time. Okay, part of the mechanism here could be thought of also as forming a double bond, and then forming a carbocation, and then taking that carbocation and connecting it over here. Okay, so it looks fancy. Okay, and then once you do that, okay, make a new carbocation over here. Okay, now with that in mind, let me back up here. Okay, and look at this picture right here. Okay, so what we're saying is that, okay, the pieces are actually what we say migrating. Okay, because this is a rearrangement reaction. Okay, okay, they actually participate in helping to support the positive charge that was developed by actually ionizing off water. Okay, because of that, then you should remember that tertiary carbocations are more stable than secondary, are more stable than primary, and definitely more stable than methyl cations like that, which have not been observed. Okay, So that's a second reason, okay, why you want to move a tertiary group over secondary, and secondary over primary, and primary over methyl. Okay. Okay. The last reason that you could give for that, also for wanting to shift those groups, okay, and all these terms are actually called migratory aptitudes. In other words, that you have different groups and you want to know which one of these actually shifts over more easily. Okay. And so the other reason for actually doing the reaction in this way is the fact that once you do your migration like this, just like this, okay, then what you've done is actually you reduce the steric congestion, okay, at what we call the migratory origin. Okay, where you're moving to is called the migratory terminus. Okay, just fancy Latinized terms like this so that you don't understand as easily what we're doing. Okay. Okay. So on these neopentyl systems, which are the ones that are given in this lesson right here, what you have to do is decide which one of the three alkyl groups gets shifted over when you remove water from the system. Okay? And why do we use these neopentyl systems? Because they're systems that really can't do anything else but doing these alkyl shifts, or they're also called cationic rearrangement reactions. And the reason why they can't do anything else is because, okay, since they're neopentyl, they're very sterically congested, so you can't do an SN2. Because they're primary, or originally primary, you can't do an SN1, okay, because there's no hydrogen next to the where we ionized off the water, okay, then you have to go ahead and excuse me, you have to go ahead and remove okay, you have to go ahead and shift an alkyl group, okay, no hydrogen right there. Okay, now once you've done that, okay, the next step of this reaction, okay, and let me go ahead and show all the hydrogens again, okay. The next step of this reaction is to go ahead and, okay, now let me move this out of the way because something funny right here happened, okay. And what happened funny is that I bonded those electrons not to oxygen, but to a hydrogen next door, not realizing that there was one there because I had toggled off the hydrogen. So make sure that this is over here. Okay. So now you have a carbocation, and so what you're going to do now is you're going to go ahead and do an elimination. And so what you have to decide is on which side to go ahead and eliminate. So let's take a look at this. Okay, let me go ahead and remove the hydrogen again because it's very busy. Okay, and so you have your carbocation right here, and so you have to decide on which side to go ahead and remove your hydrogen. Okay, and so on this carbon you have 2 hydrogens, on this carbon you have 2 hydrogens, and on this carbon you have 1 hydrogen. And so if you learned about Zaitsev's rule right there, then you should go ahead and eliminate on the carbon that has the least hydrogens, or in other words, the poor get poorer. So let me put the hydrogens back in here. Okay, and once we have that in there, then I'm going to go ahead and use chemistry to go ahead and complete the reaction, okay, and do an E1 elimination. Okay, and so that's not what we should have done. What we should have done is actually taken the electrons away from hydrogen, okay, so we can regenerate a proton. Okay, so I'll hit arrange. Okay, and now that we've done that, okay, let me move these other pieces out of the way, okay, because we don't need the water in the picture anymore, and we don't need the proton anymore. Okay, when you're doing these, because there's such sometimes some large structures like here, then you should probably go ahead and try to write down what exactly did you actually do in this whole reaction. Okay, so that's why these reactions are called rearrangement elimination reactions. Okay, and so they're not just simple eliminations. You actually have to move the carbons to other positions. So before I complete the answer, let me go ahead and remove, okay, water and the hydrogen from this picture, because I only want the product, the organic product, and I don't want the byproducts, which will be removed in the workup. Okay, so that was a rearrangement example. Okay, hopefully we'll get another one in this lesson, and it'll be simpler. Okay, here we have the elimination product of 1-butanol and sulfuric acid. So let's draw a butanol. Okay, put in our oxygen. Okay, add all the pieces. Go ahead and add an extra proton. Okay, and then we'll arrange the picture right here. Okay. Okay, after we do that, then we'll go ahead and and go ahead and move this, okay, and protonate the alcohol. Okay, and so like the neopentyl system before, okay, we just can't go ahead and ionize off, okay, water and excuse me, ionize off water and make a primary carbocation. We have to either shift something from the neighboring carbon, which it could be hydrogen. Okay, in other words, we could do this. In fact, most textbooks, okay, will go ahead and tell you that you should go ahead and get a rearrangement product, okay, where you shift a hydrogen over to the carbon right here. And after you do this, then you'll go ahead and use Zaitsev's rule to go ahead and eliminate right here to make the major product, okay, a double bond over here. Okay, but it turns out that if you're very careful, okay, and so let's go ahead and undo this. Okay, if you're very careful, okay, and you don't actually keep this reaction going for very long right here, okay, there's strong evidence, in fact there's references for this kind of reaction, okay, that as you're, okay, and let me go ahead and shift this over. Okay, let me go back over here and undo some more. Okay, as you're removing this, okay, that you would go ahead and remove, okay, a hydrogen, okay, by removing its electrons, doing something like this. Okay, so as you remove this, you would remove this. Okay, and that kind of reaction should remind you of an E2 elimination. Okay, and so as a matter of fact, what I'm going to do is I'm going to go ahead and bring in water, okay, because this reaction with sulfuric acid in there is done in water. Okay, let me put my water down here, let me add my hydrogens. And you should remember that in an E2 reaction, okay, let me go ahead and twist, okay. So in an E2 reaction, let me move this around right here so we can get everything in the right conformation. Okay, so let me twist up here. Okay, in an E2 elimination, you have to do things in an anti-fashion, okay, or an anti-elimination. What that means, okay, is that as you're having your leaving group leave, okay, which in this case will be what? Okay, water. Okay, so let me shift things around a little more. I'm using the twist function for this. Okay, what we're going to do in this reaction is we're going to use water. Okay, so let me get water over here as a base. Okay, so let's go ahead and do the E2 reaction. Okay, let me shift this a little more so we can see everything right here. Okay, so we're going to use water as a base. Okay, use it to pick up a hydrogen, and then take the electrons from that hydrogen over here. Okay, and use those electrons to kick out water. Okay, and so therefore, okay, what you can do, if you're very careful in these reactions, is you can actually just go ahead and eliminate water from the position, okay, vicinal, right? In other words, you eliminated the hydroxyl group here, and you eliminate a hydrogen over there. Now, once you form this, if you're not careful, all these reactions are reversible, okay? But once you form this alkene right here, if you have an extra proton, which we actually do from this part, from this component right here. So let me show you what can happen by having an extra proton in here. Okay, so if you have an extra proton, okay, you can reverse the process by actually adding a hydrogen to this alkene. So let me show you how that would occur. Okay, so you would take your electrons from there, okay, from the double bond, and you form a secondary carbocation. Okay, you don't want to do it in the other fashion, because in the other fashion you would form a primary carbocation. But if you do it this way, then you form a secondary carbocation, and then if you apply Zaitsev's rule, then you can go ahead and eliminate these electrons or that hydrogen from there and make a double bond. And that's why a lot of textbooks say that this is the major product. Okay? When in reality, the one I showed you before, okay, let's back up here, okay, which is what? This compound right here, okay, if you don't keep on reacting this and go back and forth like this, eliminating and adding, eliminating and adding like this, then you can actually isolate this kind of compound. Okay, so this is the kind of reaction or product that I want you to do for this reaction. In other words, we're being careful and we're eliminating the hydroxyl group from this position and the hydrogen from the vicinal position. Okay, so for this problem right here, let's go ahead and delete the extra components. Okay, and I believe there's an extra hydrogen down here, so let me go ahead and fit this to make sure we can see everything. Let me delete this extra hydrogen. Okay, and so this is what I want you to answer, right? Even if your textbook says that it's something else. Okay, so matter of fact, you have to be very careful in these reactions, these dehydration reactions, because if you let them go for very long, it'll appear actually the double bonds migrate over to another part of the molecule way beyond, you know, what you expected them to be at, like this. Okay, so the conditions and how long you do this reaction actually also determine what kind of product you get. But for this lesson, I just want you to show the direct product of doing the reaction. Okay, now we have another alcohol, and in this case it's actually a tertiary alcohol. So we'll do the same thing as in the other reactions. We'll go ahead and add a proton. Okay, and once we do this, okay, let's go ahead and connect the electrons from here to the oxygen, and we'll hit arrange. Okay, now in this case, okay, unlike the other two cases, right, where we had a primary alcohol, in this case we have a tertiary alcohol. So now it's perfectly fine to go ahead and shift these electrons over to water and make a tertiary cation. Okay, because remember, tertiary cations are more stable than secondary carbocations. Okay, so I'll move the water out of the way right here. And now I'll go ahead and use Zaitsev's rule, which means the pour get pour. Right? In this case, all three methyls are equivalent, so it doesn't matter which one we remove hydrogen from, but we'll go ahead and do an elimination. Okay, and that's how we decide which alkene to form here. Okay, we'll remove the acid catalyst, we'll remove water, okay, as byproducts of this reaction, because it's a dehydration, and we'll get that. Okay, here's another large compound that we have to decide what to do with. So let's draw butanol. At the 2 position, we want to add 2 of these. Okay, and you may not remember this, but Biz actually represents 2. Another fancy way of saying 2. So what this means is you have 2 1,1 dimethyl ethyl groups, which is just another way of saying okay, 2 T-butyl groups. Okay, because this is what? This is ethyl, and these are 2 methyls on there. And both of these are actually on the second carbon of this carbon chain. And over here, you have the same thing. Okay, you have another T-butyl group. Okay, and so this is another neopentyl system. Okay, not that it has just, you know, 5 carbons in it, and that's why you call it neopentyl. You call it neopentyl because you have a primary carbon, and next to that carbon there are just alkyl groups here. So we'll go ahead and add the hydrogens here just to make everything nice and confusing. Okay, we'll go ahead and get our acid catalyst, because all of these are using the same acid catalyst, although there are other acid catalysts that one could employ. Let's go ahead and hide the hydrogens. Okay, just so you can see everything. Okay, and what we really need to do first is go ahead and protonate this alcohol. So we'll toggle arrange, and we'll show the hydrogens, and we'll take the electrons from the oxygen, okay, and we'll use those. Okay, I think I'm doing this sideways, so I unpaired my electrons here. Okay, so let me repair the electrons now. Okay, and take the electrons not by disconnecting on this side right here, but what I really want to do is I want to connect or take the electrons from the atom and now share them with that hydrogen right there. Okay, now in a previous problem that we had like this, a neopentyl system right here, we had to decide which alkyl group to shift over, right? But in this case, it's the same alkyl group. They're all T-butyl groups right there, right? In fact, this is very congested. Okay, and I even wonder if this molecule really exists, okay, because it's so congested. So again, what we're going to do then is we're going to go ahead and ionize off water, Okay, and we don't form a primary carbocation, so what we have to do then is we have to move what? The electrons from this carbon and move the T-butyl group over to the other carbon. Okay, and this generates, okay, a tertiary carbocation. Okay, we'll go ahead and remove the water because we don't need that anymore. Okay, we'll put in the hydrogens again so you can see them all, and we'll complete the reaction by doing elimination, okay, in the Zaitsev fashion. Okay, and so doing that means you're going to what? Remove the electrons from here, okay, make a double bond, okay, and then get rid of your acid catalyst for here. Okay, now when you form your double bonds, a lot of times you'll have to decide, okay, if what configuration you should have at this carbon. So please keep track of that. Otherwise, you'll get a message like wrong diastereomer, because remember, cis and trans or E or Z are diastereomers. Okay, so we'll fit this thing over here, and I'll toggle the hydrogen so you can see what we actually did. So remember, this T-butyl group used to be over here, okay, and we relieve steric interactions by moving it over here, right? Remember also, because it shares the migrating group from one carbon to the other in this rearrangement reaction, it shares in the positive charge, right? So we want to migrate tertiary over secondary and secondary over primary, and the last thing we want to migrate is methyl, right? Okay, so this should be the product right there. Let's see what else we have in this lesson. Okay, another neopentyl type system. Okay, we have a lot of those in this system. Again, because we want to learn about rearrangements and what factors go into rearrangement. Okay, at the 2 position, we have a T-butyl group. Okay, so we want to go back and work with carbon, not with oxygen. Okay, at the 2 position, we have another methyl group. At the 3 position, we have 2 other methyl groups. So now we have to decide, should we shift over, okay, one of these T-butyl groups or the methyl? And remember, it's what? Tertiary over secondary, secondary over primary. So what I'll go ahead and do is I'll go ahead and, without putting all the components in there, I'll go ahead and remove this, because that's what we're going to do eventually. And I'll shift a tertiary group over here, which makes a what? A tertiary carbocation over here. That's the rearrangement part. Okay. Now I'll add the hydrogens. Okay, but remember, this was really a carbocation right here. Okay, so I probably should go ahead and, if an extra hydrogen was added there, let me go ahead and delete it from that position. Okay, otherwise I will not be able to explain, why I have all those other groups right there. Okay, I'll remove the oxygen because we don't need that anymore. And then we'll go ahead and do a Zaitsev elimination. In this case, this carbon has 3 hydrogens. All the other carbons don't really have any hydrogens to eliminate. So I'll shift these electrons over here. Okay, and I'll go ahead and delete. Okay, and I'll hit arrange. Okay, and if this view is too confusing, you can also go to lines and toggle the hydrogens. Okay, and if you roll this around, you'll see where the double bond is. Okay, and so again, what happened in this system right here? Okay, I moved it around so much, okay, but originally this is where the alcohol was right here. Okay, the OH group, the hydroxyl group. And this T-butyl group used to be over here. So to remove that hydroxyl group as water right here, I had to shift one of the 3 groups, either T-butyl or this T-butyl or the methyl. Remember, the T-butyl group has the greater migratory aptitude, we call it, the greater ability to shift over. So we shifted it over, which generated a tertiary carbocation, and then we had to do a Zaitsev elimination. And so this carbon used to have 2 hydrogens on it. So we eliminate it, so now we only have 1 hydrogen. Okay, which you can do by showing all the hydrogens. Okay, we'll hit continue, and let's see what kind of other question we have on here. Okay, that's another neopentyl system right there. Okay, so I want to go to another one where we can actually decide something more than neopentyl. Same kind of thing will happen here. Okay, maybe too many neopentyl systems. Another neopentyl system. Okay, I'm really hoping I can show you something else than that. Another neopentyl system. This is our last chance. Okay, 10th question. Okay, finally something different. Okay, and we have pentan 2-ol, and we have a methyl right here. Okay, and so what we'll do is, again, we'll introduce a hydroxyl group, we'll protonate it with the acid, we'll ionize off in this case, so this will be an E1 elimination because we'll make a carbocation. Okay, and then we'll look around to the vicinal positions, right, these 3 positions, and we will remove a neighboring hydrogen. And so using Zaitsev rule, we'll remove a hydrogen from here and make a double bond over here. And that's how we can know, okay, that this should be the major product right here. So let's go ahead and go and delete, and we'll go ahead and bond between here. Okay, again, if there was some stereochemistry right here, you would try to make the most stable double bond where you have the groups, the larger groups away from each other to reduce steric interactions. Now let's add all the hydrogens. Okay, and so again, we remove the hydroxyl group as water. We remove the hydrogen from the vicinal position, and we got to this compound. Okay, and again, in review, in this lesson, you'll either do an E1 elimination, or you'll do an E2 elimination of water, okay, or you'll do first a rearrangement and then elimination, okay, in the Zaitsev fashion right there. Okay, remember when you're doing those E2 eliminations, that has to do with the primary alcohols, okay, that have a vicinal hydrogen, and so we believe that we can just use water as a base to help deprotonate the position next to where the hydroxyl group is, and then make a double bond at the same time that you're removing water from the substrate. Okay, please answer those in that fashion, even though your textbook may say that something else happens. But again, remember what textbooks say, might actually be the result of further reaction.